brighter finishes, better oils, new techniques and instruments for studying, analyzing, and understanding. A search that will give us the materials and the products, the energy and the power for the future. The Research Laboratory, over 1,400 people, the largest staff section of General Motors Technical Center. 500 scientists and engineers engaged in hundreds of long and short-range projects, and in consultation and service for other GM staff and divisions. In their pursuit of advanced concepts, they advance many fields of science and engineering, sometimes with basic research, sometimes with prototype processes or design. Their search takes many roads, but almost always involves relationships between matter and energy. In probing the fundamental nature of matter, physicists are finding important clues to the relationship between structure and physical characteristics by studying the crystal, focal point of much solid-state physics research. Crystal growth is carefully controlled and documented. Shown here is cadmium sulfide, a compound semiconductor. Knowing the individual life history of a crystal helps to interpret results of later experiments. These studies are explaining differences between crystals and ways in which crystal orientation, surface impurities, and lattice defects influence crystal characteristics and the behavior of solid materials. Analysis of single, highly pure iron crystals brings new understanding of metal strength and durability. Investigation is revealing the effects of specific atomic structure and orientation on surface oxidation. These microscopic studies may help us learn more about corrosion on a larger scale. In probing methods, physicists use one of the world's few thermionic emission electron microscopes to study dynamic processes while they are occurring in metals subjected to high temperatures. Electrons boiling off a sample of plain carbon steel produce an image of the metal surface. Phase transformations become visible as the metal is cooled from a high temperature of 1950 degrees Fahrenheit, and austenite transforms to pearlite. Microscopic records like this are telling us more about mechanical properties of metal: strength, hardness, toughness, helping us develop the materials of the future. An even closer look at the grain and crystal structure of steel is made in the X-ray diffraction laboratory. Long-term studies here have provided better understanding of how residual stresses influence durability, and have yielded a novel process that greatly extends the life of highly stressed parts, such as ball bearings. Studying matter also includes investigating the interaction of matter, fundamental to our understanding of wear and friction. Physicists are probing the frictional secrets of a rolling steel ball. Rolling on a flat plate, the ball loses energy by internal friction, the dissipation of energy inside matter as molecules rub together. Rolling in a groove, it also dissipates energy due to microslip or sliding friction in the curved contact area. Accurate measurements of these energy losses are helping to extend rolling friction theory and improve mathematical prediction of losses in ball bearings. Exploring matter includes analyzing matter. The nuclear magnetic resonance spectrometer applies steady and alternating magnetic fields to a material, causing nuclear elements to resonate at certain frequencies, revealing the material's molecular structure. Here, the spectrometer identifies different components present at various stages in the formation of a new polymer. Polymers, modern man-made molecules, are being synthesized in new ways by our chemists, giving us new plastics, adhesives, rubber, paints, coatings. Ultraviolet light, electrochemical means, both are being investigated as triggering techniques for polymer reactions. To support each one of us, each year, a great quantity of material is required. For example, more than half a ton of iron. Thus, the exploration of matter and the development of materials must be accompanied by the search for better ways to preserve materials, to strengthen them and increase their capability. Materials get tired. Residual stress, vibration, loads over days, months, years, all affect fatigue life. In hours, even minutes, engineers duplicate years of operational effects, seeking fundamental data concerning the dynamics of material failure. When, how, why. For example, in a vacuum, a sample of copper is pulled apart. When the clean surfaces are pressed together, the copper re-welds itself without heat. Tests like this are providing new information about the plastic strain versus cyclic life relationship of various materials, indicating that overall durability depends on a combined failure and partial repair process, which delays the propagation of cracks. Load carrying capacity in bearings and other moving parts. This is another area being explored in depth. Some problems are solved by air bearings. A film of air, or gas, is drawn in by rotation to separate the micro-machined elements. One practical result of this work is precision low-friction bearings. Long experience in developing hydrodynamic and hydrostatic bearings is reflected in a very stiff and precise spindle for machine tools. Using externally pressurized bearings, the spindle provides machining accuracies within a few millionths of an inch, both in grinding and boring. The search continues also for better ways of protecting material against another enemy, corrosion. Various metal pairs and surface coatings are studied by means of a potential probe. This can provide data on relative resistance to electrolytic corrosion. The electrolyte solution above the material exhibits differences in ionic character, recorded as differences in potential between the electrodes. The differences in potential indicate the metal's tendency to corrode. As the ultimate test, coatings and materials are subjected to the complex and relentless forces of nature itself. At the laboratory's Florida test field, the results of years of coating research are exposed in precisely controlled programs to sun, moisture, and oxygen that do their damage 3 times as fast here as in most parts of the United States. Atmosphere affects people as well as material. In the nation's most advanced experimental smog chamber, research chemists subject automotive exhaust to artificial sunlight in order to probe the complex mechanisms that govern smog formation. A vehicle and chassis dynamometer are tied in with a 40-event programmer, which pre-selects various typical engine operations: starting, idle, acceleration, constant speed, and deceleration, during which exhaust gases can be sampled. Exhaust is diluted with pure air to the parts per million concentrations typical of determined reactions between gases from the automobile and constituents in the outside air. These studies are being applied to relationships between smog reactions and eye irritation on the one hand, and fuel composition, engine design, and car operation on the other. The long-path infrared spectrophotometer is establishing the relative concentrations of hydrocarbons and oxides of nitrogen that give a maximum rate of smog formation. One discovery: reduction of nitrogen oxides can increase smog formation. Fuel combustion in the engine itself is examined in a single-cylinder engine. A transparent piston allows the researcher to see inside the combustion chamber. Researchers here pioneered in the use of high-speed motion pictures in order to learn more about the combustion process and problems of engine knock. Recent film studies have shown how a small part of the fuel next to the cylinder walls never burns, even during good combustion, but goes out the exhaust. Fuel combustion and automotive exhaust studies are just one part of a fundamental search for better ways of releasing, controlling, and using energy. The Stirling thermal engine, invented more than a century ago. Researchers here in the Broad have improved this quiet, inherently efficient external combustion engine by applying modern theories of thermodynamics and heat transfer. Today it is capable of many stationary and mobile applications, here as a portable auxiliary ground power unit. Research engineers are also developing advanced gas turbine engines. Behind the design of a modern gas turbine are years of applied research in combustion and heat transfer to determine how to get the required heat most efficiently. In fluid dynamics, high temperature measurement, and thermodynamics to find out exactly what is going on in a moving gas stream. From this research background come further engineering calculations, new designs. Then the laboratory shops take over, versatile facilities that can transform almost any engineer's ideas into physical reality, from tiny instrument bearings to giant fatigue machines or turbine engine compressors. They can even make an entire new engine, which then is subjected to exhaustive evaluation in the turbine test laboratory. Finally come more extensive experiments in heavy-duty vehicles, where the gas turbine operates to best advantage. All is part of the continuing search. An even newer system of energy conversion is also being explored: thermionic direct conversion of heat to electricity. Physicists are developing a unique cathode which combines fissionable and emitting materials. From such advanced developments may come new power for the next generation on Earth and in space. Another possible source of new power, the fuel cell. Research on reaction mechanisms at the fuel and oxygen electrodes is showing how hydrogen or hydrocarbon fuels can free electrons to do useful work as electric current. In the search for better ways of controlling and directing energy, physicists and electronics engineers are developing many new materials: compound semiconductors, ferrites, ferroelectrics. One promising discovery: inexpensive, plentiful potassium nitrate is an excellent ferroelectric under the right conditions, responding to an electric field as a magnetic material does to a magnetic field. One possible use is in computer circuits. Another unique development: a new technique for making ferrites, iron oxide materials with desirable magnetic properties. Ferrite powders are mixed, calcined, then milled into a plastic binder to form sheets. one system, for example, a designer can call upon hundreds of sub-programs in the computer's memory to create and modify the design of a surface. Ingenious computer programming permits him to observe the surface as viewed from any angle, enlarge an area, change or delete lines, and immediately see the effects of the changes on the viewing screen. This new design system, which contains 750,000 stored instructions, greatly extends the use of the digital computer, already highly effective in statistical analysis, operations research, engineering and scientific investigation. Computers are also helping provide new understanding of vehicle motion, ride quality, steering, general handling characteristics. Ride motions simulated on the analog computer for a specific pre-recorded road surface are duplicated on the motion simulator to assist the engineer in evaluating suspension designs. In addition, engineering psychologists can investigate human response to vibration. They hope to predict how customers will react to the ride of cars still on the drawing board. Frequently, a search for quantitative understanding requires sophisticated, even new mathematics that provide fresh approaches to the approximation of functions, mathematical representation of surfaces, and statistical theory. As in all disciplines, there is here a continuing exchange, shared with the national and international scientific and university fellowships, through annual symposiums and seminars, exchange visits, and through frequent publication of research papers. Theoretical and experimental investigations are also being applied to the problem of traffic flow. Experiments with single-lane traffic streams, like this platoon of buses, have provided supporting data for mathematical models.